Welcome back, everyone, to this explainer on system development. Okay, let's dive right into today's vital topic by contrasting this massive hardware-intensive process with the nimble, agile software coding we've discussed previously. Today, we're putting on our professional engineering hats to look at the architecture of large-scale systems where physical hardware, complex software, and multiple independent contractors all collide. We're transitioning from simply writing code to building monumental socio-technical systems. Here is the agenda for today's program. We'll start with an introduction to system development, move into the 7 key development activities, explore the requirements and design spiral, discuss integration and the infamous blame game, and finally wrap up with a comprehensive lecture summary. Section 1. Introduction to System Development Beyond Agile. Let's see how this builds on everything we've learned so far. First things first, we must define what system development actually is. It is the complex process where system elements like hardware, software, and off-the-shelf components are developed, purchased, and integrated to create a final working system. You can really think of it as the critical bridge between your conceptual design, the ideas on paper, and the actual physical realization of the system. It's where the system is actually built. Now, this is a crucial point that you really need to recognize. Unlike pure software development, which absolutely thrives on agile iterations, massive systems almost always require a plan-driven waterfall model. Why is that? Well, because when you're dealing with physical hardware and multiple external contractors, making changes late in development is incredibly expensive, or honestly, sometimes practically impossible. You literally cannot just recompile a physical piece of hardware if you make a mistake. Strict planning is absolutely required. So just to quickly recap, massive physical systems demand strict, linear waterfall planning, which completely shifts us away from our usual agile mindset. Section 2. 7 key development activities. The blueprint. We are now entering a highly testable area of our program today. Take a look at figure 19.10. It brilliantly illustrates the linear flow of the 7 steps we are about to break down, moving clearly from left to right. Notice the overarching waterfall structure here, but pay special attention to those stacked concurrent boxes in the middle. This represents how different contractors actually work in parallel to build the system. Let's walk through each step carefully. Step 1 is requirements engineering. In this context, it's the process where we refine, analyze, and rigidly document the high-level business requirements that were merely conceptual earlier on. We absolutely need to lock down exactly what the system needs to achieve before any physical building takes place. Moving on, step 2 is architectural design, which, as you'll see, heavily overlaps with requirements engineering. This is where we begin structuring the physical and digital system. We establish the overall architecture, clearly identifying the different system components, and deeply understanding the complex relationships between them. Step 3 is requirements partitioning. Here, we must categorize tasks and assign them to specific subsystems to minimize any critical overlap. Basically, we look at a single requirement and ask, okay, is this solved by a physical piece of hardware, a software module, or maybe by changing human operational processes? We partition the requirements accordingly. Step 4 is subsystem engineering. Now, a very common misconception students have is that one giant team builds absolutely everything. But here, multiple contractors build separate parts concurrently. One contractor might be busy developing software, while another is configuring off-the-shelf hardware, all running in parallel based exactly on the architecture we designed. So looking at the full picture, here are all 7 steps. After the contractors finish step 4, we move to step 5, system integration, which is the process of putting all those independent parallel parts together. Then, step 6 is system testing, an extended activity designed to find the bugs and tune performance. And finally, step 7 is system deployment, where we go live and make it available to the users. To recap this vital phase, we engineer requirements, design the architecture, partition tasks, build subsystems in parallel, integrate, test, and finally deploy. Make sure you memorize this exact sequence for your exams. Section 3, requirements and design spiral, the nuance. Let's transition to a concept that introduces a bit of nuance and challenges that strict linearity we just looked at. We need to define the requirements and design spiral carefully. Even inside a rigid waterfall process, the initial phases of requirements engineering and architectural design must be interwoven continuously. As shown in figure 19.11, they definitely do not happen in isolation. The underlying logic here is actually pretty fascinating. You simply cannot finalize what a system is required to do without knowing what the physical hardware architecture is actually capable of achieving. And conversely, you can't design the architecture without knowing the exact requirements. Discoveries in one phase inherently force changes in the other. In short, remember that requirements and design are a continuous, concurrent loop, a spiral, not a one-way street. Section 4. Integration and Blame Game, the Danger Zone. Welcome to the physical building phase, where theory finally meets reality, and the risks of catastrophic failure multiply rapidly. Before we explain why it's so incredibly dangerous, we must define Big Bang integration. Big Bang integration is a highly risky approach where you take all independently developed subsystems from your various contractors, bring them into one room, and just plug them all together at the exact same time. Here is the critical takeaway. You must always use incremental integration. Think about it. If you use the Big Bang approach and the system fails, which, let's be honest, it almost certainly will, you have absolutely no idea which of the 100 subsystems caused the crash. The errors are completely untraceable. Incremental integration, on the other hand, safely adds one piece at a time, cleanly isolating errors step by step so you can accurately diagnose any problems. Furthermore, during system testing, human behavior plays a massive, massive role. The textbook notes that when a crash occurs between two subsystems built by different contractors, they will predictably blame each other. This infamous blame game leads to massive delays and endless negotiations between contractors just pointing fingers. You must anticipate this socio-technical challenge as an engineer. So remember to recap this danger zone. Always avoid the Big Bang to keep your errors traceable and anticipate human friction during testing. Section 5. Comprehensive Lecture Summary. Let's wrap up with a rigorous recap of the essential facts you need to recognize for your final assessments. All right, here are your absolute key exam takeaways. First, ensure you can list the 7 development activities in strict sequential order. Second, you must understand exactly why the Big Bang integration approach is highly dangerous compared to a safe, incremental approach. Third, recognize the nuance of why requirements and design form an interwoven spiral, despite being part of an overall plan-driven process. Getting these concepts down perfectly sets up our next explainer on system operation and evolution. Right before we end today, I want to leave you with a provocative question to chew on regarding human behavior in engineering. If technical errors are literally inevitable, how can we proactively design our engineering team structures to minimize the damage of the blame game? Reflect on that socio-technical challenge before we meet next time. Thank you so much for studying with me today, and I'll see you in the next one.